So what we've seen is that quicksort performs badly on arrays that are already sorted or arrays that are sorted in reverse order. So it's worth thinking about exactly why this is the case, right? Why was it that quicksort failed so badly to sort this thing quickly? And so remember, with quicksort, the thing that makes quicksort fast is if it splits the array into roughly equal size pieces. But by giving it a sorted array, and by our particular rule of pivot selection, we've actually forced quicksort to split the array into maximally unequal size pieces. Okay, so let's think about what the right pivot would have been. Right? What is a good pivot? Well, remember the pivot is a number, right? It's a number, right? Think of it as a number that should, ideally should belong somewhere in the middle of the array. So the ideal pivot, if I have a sorted array as my input, the ideal pivot to select would actually be the middle element, right? Why the middle element? Because if the array is sorted, that belongs in the middle. Okay, so we'll have to be really clever about how to select a pivot that we have some expectation belongs in the middle for an arbitrary array. But at least for a sorted array, we can see that if we were to have somehow picked the number 3 as our pivot for a sorted array, then we would have been in good shape. So we'd have to modify the Hoare partition slightly to be able to pick a different pivot. But let's think a little bit about what that would look like. Just on this simple 5-element array for 5. So suppose we pick our pivot to be the middle element, right? The center, numerically speaking, the center of our array, the median element of our array. Well, then how does this work? Well, we still set up I and j counters, right? We still set I here and j here. We still have the counters walk towards each other, looking for something that doesn't belong. And here, again, doesn't belong means is bigger than or is less than the pivot value. So what I will do is I is looking for something that is bigger than the pivot. So it'll walk forward until it finds the pivot itself. So I pauses on the pivot. J will walk down looking for something smaller than the pivot. And so what will it do? It'll stop on the pivot because it's found something now that's less than or equal to the pivot. And so now I and j have both paused. They're looking at the same element, which means that they overlap. And so what do? We swap the pivot with j, and then we return. Well, the pivot equals j, so we're done. Right? And so now we go to our next step, and we have 2 arrays left to sort. We've identified the location of that element. And all we have to do is deal with these 2 arrays here on the side. And so here now we have a perfect split, right? By choosing the median element in the array, we have a perfect split for quicksort. And so now quicksort will terminate in the next step. And the precise details of how it handles those 2-element arrays are not that interesting. But in the next step, it will correctly identify the locations of all the remaining elements. And so whereas the recursion would have to be 4 or 5 deep for our original array if we used the lazy pivot selection, if we did a smart pivot selection that happened to get it right every single time, happened to pick the median element in the array every single time, then we'd end up terminating in only 2 recursions, right? It'd be much more quick, much faster. All right, so the question then is, since we don't know what these arrays look like to begin with, how can we select a pivot that has some likelihood of belonging in the middle of the array, right? That's what we need to do. We need to select a pivot that has some likelihood of belonging in the middle of the array. So how to select pivots. Well, so this actually ends up being one of the core questions about optimizing quicksort. And there's been a lot of work trying to come up with what are the right pivot selection methods. And here's a really simple one that works pretty well, right? So here's one possibility. I'm going to call this answer number 1. So answer number 1 says, go look at the first element of the array, look at the center element of the array, and look at the last element of the array. right? Compare those three values, and then pick the median of them, right? Pick the one that's in the middle. So this is called median of 3. Of 3. So if you pick the first, so if I have some massive array, I've got A0, dot 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 dot, and then here I've got A n over 2. And let's floor it so that we don't get an indexing error. And then up here we have A of n minus 1. Okay, so those are 3 different numbers. They're drawn, you can almost imagine them as having been drawn randomly from the array, right? And so the middle one has, we know that the middle value of these, and I don't mean, in terms of its index, I mean the one that has the value that is in the middle, right? So maybe this one's 10, maybe this one's 100, and maybe this one's 0. Right, what would we choose? Well, we would choose this one. We would choose the median value of these 3 things. So what do we know? Well, we know we're guaranteed now that it's not the smallest number in the array, because we know that 10 is bigger than those 2. We're also guaranteed it's not the biggest number in the array, because the biggest one is here, is at the end. So we have some now expectation, or I should say anticipation, that the pivot we've selected using this pivot selection rule belongs somewhere in the middle of the array, right? So now we have some likelihood. I'll try not to use super technical language here. We have likelihood that our pivot belongs in the middle somewhere. Okay, and we almost have a guarantee that the pivot does not belong at one of the 2 ends, which would result in an unequal split. Rather, we have some reasonable possibility that the pivot belongs somewhere in the middle. Okay, so here's another possible answer. Okay, just pick a pivot randomly. Right, pick pivot randomly. Okay, and so this is actually a very, very deep idea that we're not going to be able to get into much depth in this class. But the idea of picking a pivot randomly is that every single time you just draw a number out of the hat, a number between 0 and n minus 1, and then use the value that's in that location as your pivot. Okay, so why is picking a pivot randomly a good idea? Well, this makes it so that it makes worst case inputs extremely unlikely, right? So what we're doing here is we're using randomness. We're using randomness to, and I like to think of it this way, to foil worst case inputs, right? So to avoid worst case inputs. So one way I like to think about this, and this can be a useful analytical kind of device, is I like to think about inputs as coming from some enemy, right? We have some enemy out there that is generating inputs for our algorithms, and when we're doing worst case analysis, the enemy is trying to always give us an input that makes the algorithm run badly. Okay, so suppose now that we have this thing that we do where at every step of the algorithm, we just flip a coin and do something random, and when I say random, I mean something that the enemy cannot predict. What does that do? It makes it very, very difficult for the enemy to give us a worst case input, right? It makes it more likely than not that the enemy's attempt to give us a worst case input will fail, okay? And so this is quite common in algorithms, and it turns out there's actually lots of ways of using randomness to improve the performance of our algorithms and to write really good algorithms, really fast algorithms. And this is an example of this, right? So the idea is, the inputs that caused our algorithm to run badly had this very fine structure. And so by adding this randomness, by picking our pivot randomly, we disrupt that structure. And it doesn't take a huge disruption to make that structure meaningless, right? To make it so that it doesn't hurt us anymore. So, we can say, use the randomness to avoid worst case inputs, or observe that worst case inputs have very fine structure. Have fine structure. Okay, and so this is another actual true pivot selection technique that works in the real world in Quicksort. And so here our randomness is, it's like we're adding a little bit of noise to disrupt that fine structure, right? So the randomness disrupts structure. Okay. And so let's think a little bit, just briefly, about what it means to disrupt structure, or what else we could do to disrupt structure. And so here's a third one, which is not a practical answer, but it's a true answer. And the third one is just scramble the array at the beginning, right? So you get your input array. You're worried that it could cause you to run in worst case. So the first thing you do is you just mess with it, right? You just go, and then you run Quicksort on it, right? What we're saying here is that on average, doing this to your array before you try to sort it might actually make the algorithm run faster. Okay, just scramble the input array. Right, and so I do want to make sure that it's clear that A2 and A3 accomplish the same task, right? They're both ways of adding randomness to the algorithm. A2 is much more efficient. So A2, all you need to do is pick one single random number each time. A3, you have to come up with some way of scrambling the array, which is not likely to be a super fast operation, right? So this is not practical, but it's instructive, right? So the idea is Quicksort will perform better on average on random arrays than on highly structured arrays. So not practical, but instructive. All right, so this essentially brings us to the end of our discussion of Quicksort, and I just want to mention, and I'm not going to prove this, but I just want to mention that if you use smart pivot selection techniques, or if you always give Quicksort random arrays, Quicksort has a very fast average case complexity. So Quicksort, we know already the best case is n log n. We know already the worst case is n squared, but it turns out that it's actually kind of hard to make it run in n squared time, and that on average, the complexity is actually n log n. Okay, where on average here means on random inputs, right? If I just always give it randomly sorted arrays, or I use some kind of a smart pivot selection technique, I'm typically going to have n log n complexity. So that, coupled with the fact that Quicksort is in place, which makes it very space efficient, makes Quicksort an excellent sorting algorithm, right? And it's time competitive with merge sort, and it is in place, unlike most implementations of merge sort. So Quicksort can be quite a powerful way to go if you're trying to sort numbers.